Hello, this is Group 2. Our focus is on predictive analytics of water quality in Alberta. We like to have better understanding of the different state of water quality in the province. And the members of Group 2 are Dylan Chappelle, myself, Ehimai Oyosebao, and Yusuf Tantowe. We hope we are able to walk you through our findings and you get some learnings from it. Thank you for joining us.
So the primary objective of our project is to analyze extensive water quality data to reveal patterns and trends. So we're especially interested in spotting anomalies that indicate environmental risks and identifying areas where intervention might be needed. This forms the foundation for better decision making and policy development. So to guide our analysis, we developed several key questions. These include evaluating the overall health of Alberta's rivers, identifying hotspots of pollution, and checking whether there are certain water quality indicators often deviate from norms. So we also looked for correlations and temporal patterns. So the key questions. The key questions to answer: what is the general state of water quality across Alberta's river basins? Well, this varies significantly. Some river basins, especially in the south, show higher concentration of contaminants like phosphorus and heavy metals. Second question: are some stations or sub-basins constantly exceeding safe thresholds? Yes, outliers were found in iron total recoverable, with the max was 73,600, and sodium dissolved, the max was 34,000, suggesting pollution hotspots likely tied to industrial activity. And third question: which parameters show critical deviations? Parameters with extreme ranges and high standard deviations include iron total recoverable, lead total recoverable, sodium and potassium dissolved. While pH and dissolved oxygen weren't among the most frequent variables, they're still essential indicators. In Alberta's monitoring, deviations in DO can signal ecosystem stress, especially during warmer months. And now, next question: are there seasonal or year-to-year changes? Well, this is an undergoing analysis that we plan to look at later on. But time-stamped data supports future trend modeling. For example, seasonal drops in DO or spikes in conductivity during snowmelt runoff. Next question: are some parameters correlated? For example, like conductivity in dissolved solids? Yes, the correlation heat map revealed strong positive relationships between similar metals. For example, iron dissolved versus total, and moderate links between sodium, magnesium, and conductivity. This indicates shared sources or chemical behaviors. We didn't just frame these questions, we answered many of them through deep data analysis. And we found Alberta's river quality differs widely by location, as certain parameters like iron and sodium spike dramatically at some stations, possibly linked to industrial or agricultural discharge. While pH and DO were not the most frequent measures, they remain biologically crucial. Future modeling with time series data will help reveal long-term trends, and correlation analysis showed that some contaminants tend to appear together, hinting at shared sources. So, why is this important? Understanding water quality isn't just academic, it has real-world applications. Safe water is essential for both humans and animals. By identifying risks early, we can implement protective measures. This also supports evidence-based policy making to ensure long-term sustainability. Our analysis is based on a comprehensive dataset containing over 143,000 records across 30 different fields. These fields include geographic, temporal, and chemical information, allowing us to conduct spatial, seasonal, and parameter-specific analysis.
We got our data from Alberta dossier. Essentially, it has information, very good information of the state of the surface water quality of the different watersheds and river basins in the province. In all major cities and towns and villages in the province, they have monitoring stations at different locations, and that stations collect surface water quality data, different kinds of data set and parameters. And so one of the first things that we did was first to define the scope of work. Because if we were to use just the data set that all the data set that we found on the website, that would mean going back even to the 1940s and 50s and several records and lots of parameters. Like several that this is what many PhDs are required to do. And considering that we have very limited timeline, we needed to scope the work. And so our scope of work was focused on the data set from the January 2023 to December 2023. That helped us to zero in on a particular timeline to still be able to get the data set that we needed for that time period. Having zeroed the scope of work to the data set from 2023, we still got a very robust data set to work with. We had over 4,000 samples to work with, and in those samples, we had the different variables. And some of those variables involve the time set, the location of the monitoring stations, the type of methodology that was used to analyze the data set, the parameters that is available, the timestamp, the longitude and latitude coordinates of the area, and several other records. And our interest, therefore, was to say which of these among the many that we want to focus on. And looking at the measurement that was available, the focus then was to look at meters and have better understanding of the values and detections and readings of the meters in the surface water quality data. And that's how we decided to focus essentially on that. Having been able to identify the scope of work in a way that is manageable with the short timeline that we had, we needed to come up with the data analysis step. Like I mentioned, we needed to clean the data because there were some readings that had error messaging. We needed to remove that. There were some readings that didn't have any record. We also needed to account for it. And the first step was to clean the data in such a way that we can format it and fit it for use in the Jupyter Notebook. And so that took a bit of time in preparing the data set to be used. Once that was used, we were able to use the Python coding through Jupyter to understand the frequency of count of parameters, in this case of the meters that we're interested in. Then also be able to generate summary statistics and identify visualization techniques that would be relevant and meaningful to us. And having done that, then we did some heat maps to have better understanding of whether there is correlation in some data set or there's divergence. Then we also use the Jupyter Notebook to determine whether there are errors and outliers in the data set. And these were the key steps that we followed in performing our data analysis steps to be able to get the results that we are presenting shortly. Yeah, this is just a quick example of one of the coding that we use to understand the potential for outlier in the data set. And we have all the codings available in Jupyter Notebook that we uploaded here as well. And to be able to determine for the result to generate whether there's outlier in the system. And that was very helpful because we found some of those outliers and helped us to discover the state of the data set. Yeah, now to the results session. One of the first output that we wanted to generate was to understand the 10 most measured variable. So the best way to put it in context was there were several variables in the data set that we use. It were way up over 200, 300, but we wanted to generate the 10 most measured variable based on the different counts, and the one that came out on top was iron. Ion dissolved was the most measured, followed by or almost the same as manganese dissolved. And so those were the two critical most measured variables, and it became the basis for our analysis because that's where we focus our analysis on to have to understand the trend and to be able to do some of those statistical analysis on those two, the iron dissolved and manganese. Of course, there were some others as well. They had dissolved sodium, magnesium, total iron, antimony and lead, and others as well. But these were the 10 that were most measured, and it became very meaningful to zero in analysis on the first two to be able to come up with some understanding of the data set. Having identified iron and magnesium as a key parameter, we decided to focus our analysis on those two to be able to have understanding of some of their trends and distribution. And obviously you can see that iron using histogram, generating histogram from the Jupyter Notebook, we can see that it has very high frequency of measurement, and the measurement is very skewed to a particular year, rightfully so, because the year that we're looking at was in 2023, but it was very high in terms of the measurement across the different basins in the province. And that's fundamental for us knowing that it's a key parameter of interest. There's something common about iron across the province that is being measured and needed to be understood by the public. We did a quick time trend analysis on iron, and just looking at the measurement within the year in view, which is 2023, you can see that there was progressive increase of iron measurements over that time period. First quarter, there was minimal measurement, which is understandably so because that's about the winter months. And then as we moved into the spring month, there was increase in iron concentration, which increased significantly over the summer months and towards fall and late fall. And that's some discovery to know that there is increased elevation of iron across the province in time period, and then to understand that observation there must be a cause. Perhaps it could be because of the melting snow, and what does that mean with the rock formation that is being washed down, and other potential sources of iron in the province. But for sure, this findings shows that there's an elevated increase of iron over time within the year in view. We decided to use Python and Jupyter to generate a heat map to understand if there's correlation between iron and other metals. And based on the outputs, there's some correlation between iron and other metals like magnesium, like sodium, and even antimony. But most noticeable is the relationship between iron and total recoverable antimony. They were very correlated, actually the same in terms of 1, and that means any particular trend or pattern that iron demonstrates can be attributed to antimony. Likewise for other parameters as well, and it's very fundamental because we wouldn't need to necessarily compute the same analysis for antimony if we already have values and output for iron. It can just be extrapolated. So in terms of our findings, the most frequently monitored variable was iron and manganese. Then there was some skewness in metal concentration. We also saw clear correlation patterns between iron and antimony, as well as with other metals as well. We discovered an outlier that was more than 70,000 milligram per liter, which was totally different from the trend, and that was an outlier, maybe because of an error in the system, but we discovered that as well from the analysis.
All right, hello there. So my name is Dylan. Thank you, Yusuf and Ahimai, for the great overview and analysis there. Unfortunately, I'm under the weather right now, so I'm not going to be on camera, but I'm excited to walk through some of our key recommendations here we've developed based on the data. So after analyzing over 140,000 data points from water monitoring stations across Canada, or across Alberta rather, we have found clear evidence of pollution spikes. These spikes don't seem to be random. They tend to happen at certain stations and times of the year, which would suggest the need for targeted monitoring and responsive action. Our findings here point toward specific areas where improvements in testing frequency and predictive modeling could have a real environmental impact. So firstly, our time series analysis shows seasonal trends of the two main parameters we looked at, which is iron and manganese. I would have thought they'd behave similarly, but as you can see in the graph on the bottom of the slide here, they're very different. Manganese begins rising basically at the start of the year, peaks around February, and then stays pretty elevated until end of May, beginning of June. Iron, on the other hand, is pretty low during the winter. As you can see, it doesn't really start going up until March, but then, between specifically April and October, there's a lot of sharp peaks in there. So these fluctuations are pretty significant. Whether there's a process behind it like say seasonal runoff or something like that, or just our current monitoring maybe isn't frequently enough to catch what's really happening. Like it seems a little odd with the iron to be so up and down as it is, but maybe it is. So definitely our first recommendation is just the increase testing frequency, just to get a clear idea, a clear data, and really find the cause here. So while the the increased timing is definitely important, so is the location. So our geospatial analysis revealed a few hotspot regions, as you can see on the map here, particularly near the Saskatchewan border, and then there's a station you can see on here, kind of southeast of Edmonton. So those two locations seem to be pretty consistently reporting values far outside the typical range, especially for iron. So our second recommendation is just increased testing, especially in these high-risk areas. Just makes sense, not only because of the elevated levels, but also because they may help identify larger regional pollution trends earlier. Our third and final recommendation we have is using time series modeling to anticipate future spikes. So instead of just reacting to high readings after they get to dangerous levels, predictive analytics can help give us early warning signals. Originally, this is something we wanted to build into our project, but just with the limited time and data we had to put this together, it wasn't really feasible. However, with increased testing at specific locations, we certainly could develop predictive models that would give policymakers a head start, whether it's to schedule inspections at times expecting to have high levels, or tighter regulations, or maybe even just notifying nearby communities when the risk is expected to rise. So this kind of proactive monitoring could help really get these spikes under control before they become an even bigger problem than they are now. Really, at the end of the day, our goal is to be more environmentally conscious. So by identifying the where, the when, and the why of these water quality issues, we can protect our ecosystems and ensure clean, safe water for people across Alberta. Whether it's through better monitoring, smarter forecasting, or quicker responses, our goal is a water management strategy that's informed by data and grounded by sustainability. So thank you for taking the time to listen to our presentation, and hope you have a wonderful day.